Okay. Hello everyone, my name is Sadegh. I have PhD degree in physical chemistry. I have graduated at Ferdowsi University of Mashhad, Iran, in the field of computational chemistry. I'm here to talk about computer-aided design of nanoscale materials for biology and medicine. Biosensors play an important role for many applications, such as sensing illicit drugs, medical communities to remove overdose medications from the human and animal body. Besides, drug delivery systems are theoretically being proposed for many years and then experimentally found to deliver the drug to the targeted sites by reducing the harmful side effects. For example, in current COVID-19 pandemic, biosensors can play important roles to remove drug during the human trials if they show any unwanted adverse effect. Therefore, before proceeding to these expensive research works, advanced theoretical methods can provide to possible outcomes with considerable accuracy. Generally, most of the electrochemical sensors consist a receptor where the interaction of a biomolecule takes place and a transducer which converts this data into electrochemical signal. And finally, an amplifier to amplify the signal into a detectable one. While investigating the capability of a nanomaterial to perform as a biosensor or drug delivery system using experimental instrumentation provides with a reliable result, it often comes with a high cost and should be executed with a very low risk of failure. Hence, to minimize the risk before proceeding to these expensive experiments, a cost-effective and less time-consuming solution can be a theoretical investigation on the desired properties of the materials through computer simulations. The scarcity of nanoparticles can be used in targeted drug delivery at the site of disease to improve the uptake of poorly soluble drugs, the targeting of drugs to the specific site, and drug bioavailability. Engineered nanomaterials hold significant promise to improve disease diagnosis and treatment. Nanotechnology could help overcome the limitation of conventional delivery from large-scale issues such as biodistribution to a smaller scale barriers and intracellular trafficking through cell-specific targeting, molecular transport to a specific organ, and other approaches. The scarcity of clean water sources leads to many scientific and technological advancement in wastewater treatment processes. Existence of heavy metals in wastewater has been proven to be a challenging concern. Therefore, there is a need for more water treatment technology to completely remove heavy metals down to a non-hazardous level. The water treatment for wastage removal can also be achieved by absorption of a adsorbate in the form of liquid or gas on a solid surface, or adsorbent through a formation of a chemical or a physical band. These techniques is considered to be very useful, feasible, and cost-effectiveness. There is a significant increase in the drug absorption and heavy metal removal in the last 20 years. Density functional theory calculations become more reliable over the years on predicting various properties of a nanomaterial with a close resemblance to the experimental outcome. Besides, with the fast calculation power of modern computers, first principle calculations based computer simulations also provides a facility to investigate a lot of quantum mechanical information about biological systems theoretically at first place. From the optimized geometry, it is possible to calculate the bond length and bond angle between constituent atoms in the structures. The different vibrational mode of the constituent atom of material can be observed through the IR infrared spectroscopy. By investigating the imaginary frequencies in the IR spectrum, researchers also achieve the information about the stability of the nanostructures and the possibility of finding them into nature or synthesizing them into the lab. To investigate the structural stability of a nanostructure system, the cohesive energy of nanostructures should be calculated using equation 1. In this equation, N is the total number of constituent atoms of the nanostructure. B represents the different constituent atoms of the nanostructure. Spectroscopic properties. UV visible spectrum usually provides information about the range of wavelengths of nanomaterial. The spectrum is also associated with the electronic band gap of the material, where broader spectrum represents a wider band gap of material. Besides, it is also useful to investigate the interaction of biomolecule or drugs with the nanostructure as an introduction of the new energy states. Moreover, the redshift due to the drug or metal ion adsorption indicates a decrease in the band gap or increase in the conductivity of nanomaterials as a sensor devices. The NMR usually allows researchers to investigate the magnetic field around an atomic nucleus. However, it is further applied extensively in structural biology to study the structure and dynamics of a biological sample. Adsorption properties analysis. To investigate the adsorption process between the adsorbent and adsorbate molecule, one of the most reliable and often used method is examine the adsorption energy values. A negative value for adsorption energy represents a stable adsorption process, whereas a positive value represents no adsorption process. Besides, if the absorption process, if the adsorption energy value is less than 1 electron volt, the adsorption process is considered as weak physisorption, and no chemical bond can be found between the adsorbate and adsorbent. But if the adsorption energy exceeds 1 electron volt, a strong chemical interaction is considered to have occurred. Several important information about the adsorption can also be found from the minimum distance between the adsorbate and adsorbent. A smaller distance between the adsorbate and adsorbent often lead to a higher charge transfer between the adsorbent and the adsorbent molecules. Thermodynamic parameters analysis from the definition of the Gibbs free energy, according to equation 3, a negative change between the adsorbate and adsorbent is desired in case of both drug delivery and metal ion sensor applications. A positive change in the enthalpy, based on equation 4, labels reaction between the adsorbent and adsorbate as an endothermic reaction, whereas the negative change in the enthalpy lead an exothermic reaction. In the most cases, the change in entropy become negative due to the adsorption of a drug molecule by an adsorbent material, which is a constrained movement of the structures due to their newly formed intramolecular bondings. Frontier molecular orbital analysis. By definition, a smaller energy band gap represents a higher conductivity, which is desired for a drug sensor devices. Therefore, to inspect the sensitivity of the adsorbent towards the adsorbate, change in the energy gap due to the adsorption plays an important role in designing an electronic sensor. Density of a state spectrum, vital application of density of a state plots for the drug sensor devices is that the interaction between the drug and adsorbent can also be confirmed from the alteration of the dose spectrum due to the adsorption of the drug molecule. Another parameter is work function. Work function can be described as the minimum energy required to remove an electron from a material. The negative value of the Fermi level energy represents the work function of a system. Global reactivity parameters. The chemical potential can be used to determine the stability of the investigated structures and determination the direction of electron transfer from adsorbate to adsorbent. Another index, chemical hardness. The resistance of a structure towards the deformation can be investigated from the global chemical hardness, which can be calculated by equation 9. A higher value for global hardness indicates higher chemical stability and a lower chemical reactivity for the structure. Electrophilicity index can be used to investigate the structural stability, reactivity, and toxicity of a nanostructure. Where an increasing value, the electrophilicity index, indicates an increase in the chemical reactivity. Effect of solvents. The solubility and stability of a nanostructure in any solvent medium can be further investigated in terms of the solvation energy. Negative solvation energy of a nanostructure in a solvent medium represents a spontaneous solvation process and higher stability of that nanostructure in that solvent. In both drug release mechanism in both drug delivery and drug sensor devices, the drug release mechanism plays a crucial role to study the efficiency of the sensor. This can be observed from the interaction of the drug molecule with adsorbent in the targeted environment. If the absorption energy of an anti-cancer drug on a nanostructure decreases or become positive in the low pH cancerous cell, because the environment around the cancerous cells are acidic. The nanostructure can release the drug ideally in a low pH environment. Another parameter is very important. Recovery time. Recovery time means required time for a complex system to return to its initial state by releasing drug molecule, which can be calculated using equation 12. For sensor applications, less recovery time is crucial to release the drug quickly, which a less negative value for the adsorption energy is also required. Hence, weak physisorption of the drug molecule with the nanostructure is favorable for the drug sensor applications. DFT study of selenium-decorated B12N12 nanostructure as a possible drug delivery system for cyclopyrox. In this work, the effect of selenium decoration on the interaction of cyclopyrox drug as an anti-cancer drug with B12N12 nanocluster was investigated using density functional theory calculations. It was found that the selenium decoration significantly improves the reactivity of B12N12 towards anti-cancer drug. A short recovery time was predicted for drug desorption from nanocluster surface. Moreover, electronic properties analysis showed that energy band gap of nanocluster is significantly reduced after drug adsorption. Next paper is about first principle study of the binding affinity. First principles study of the binding affinity of monolayer B6N nanosheet, implications for drug delivery applications. The adsorption properties and most possible interactions of hydroxyurea, 5-fluorouracil, carmostin, 6-mercaptopurine, ephosphamide, and chloromethine anti-cancer drugs with B6N nanosheet were explored using DFT calculations in both gas phase and water solution. The most stable structures was observed for the 6-mercaptopurine GB6N complex. The values of adsorption energy showed a slight increase in the stability of drug nanostructure complexes by the inclusion of water solution as a preferred environment for drug delivery systems. In this work, density functional theory and time-dependent density functional theory calculations were fulfilled to investigate the adsorption behavior of amphetamine drug molecule on the pristine aluminium, gallium, carbon, silicon, and germanium zeolitic imidazolat B12N12 nanoclusters. The adsorption analysis demonstrates that carbon-doped B12N12 ZIF8 has the strongest interaction with the binding energy of 194 kilocalorie per mole in the gas phase. The calculations in the various solvents reveal an enhancement in the amphetamine drug adsorption on the nanocluster with the increasing polarity of the solvent. In the next work, DFT insight into some toxic heavy metals, adsorption onto surface of ball-like B30 nanosheet. Contamination of water resources by heavy metal ions is a drastic environmental concern. In this study, the interaction of cadmium, mercury, lead, tin, arsenic, antimony, and chromium metal ions onto surface of the ball-like B30 nanosheet was studied based on density functional theory calculations. Adsorption energy values revealed that the arsenic 3 positive interacted better with B30 nanosheet in comparison to other metal ions. Adsorption behavior and sensing properties of some toxic gas molecules onto platinum and beryllium clusters. The adsorption characteristics of some toxic gas molecules, including carbon oxide, sulfur oxide, nitrogen oxide, ammonia, methane, and ozone, onto platinum and beryllium cluster were investigated using DFT calculations. Adsorption energy analysis revealed that when platinum beryllium clusters interact with gas molecules, the absorption energy of all gas platinum and beryllium complexes decreases with cluster size increasing in general tendency. It was discovered that carbon oxide, sulfur oxide, nitrogen oxide, ammonia, and O3 gas molecules are highly chemisorbed onto platinum-5 beryllium cluster, whereas methane is physically adsorbed onto cluster. The band gap variation as a result of interaction with NO gas, nitrogen oxide gas, were found to be 31.37%, indicating that platinum-5 beryllium cluster has high sensitivity to nitrogen oxide gas molecule. The results of this work has been submitted in the Materials Today Communications recently. Thank you for your attention. Пожалуйста. Пожалуйста. Thank you. Thank you. Thank you. That's kind of you.